Hi guys, this is lesson 13.5 for conjugate roots and Descartes' rule of signs. Our objectives for the day are to use the conjugate roots theorem to solve an equation and to determine all of the possible combinations of roots of a polynomial using Descartes' rule of signs. So let's begin with the conjugate roots theorem. So if we have f of x, a polynomial, all of whose coefficients are real numbers, and we know that a plus bi is a root of the equation f of x equals 0, then a minus b, its conjugate, is also a root. In other words, complex roots must come in pairs. Okay, complex roots come in pairs. Now, the irrational roots theorem states that if f of x is a polynomial, again, whose coefficients are real numbers, and we know that a plus b root c, so here's an irrational root, is a root of the equation, then a minus b root c, its conjugate, is also a root. All right, so let's begin with problem number 1 here that says to solve this equation given that 1 plus 2i is a root. Now remember that if 1 plus 2i is a root, then you know one of two things. One, you know that x minus 1 plus 2i must be a factor, so you could, if you wanted to, use long division here and try to find the resulting polynomial. But you also know that you have another factor, a minus 1 minus 2i. Its conjugate is also a root, right? So we have an additional factor here. So you guys actually have two options here to solve this equation. With one option, you could take both of your roots, 1 plus 2i and 1 minus 2i, and you can use synthetic division to find the resulting polynomial. Okay, so I'm going to show the work for this. I'm going to take 1 plus 2i here, and I'm going to show the work. I'm going to actually pause because this is going to be a ton of work to do, and once you guys see the actual problem worked out, you're going to see why I paused instead of making you sit through the whole thing. Okay, now after doing synthetic division here, I end up with this polynomial here. Now, I should get a remainder of 0 because I know that this is supposed to be a root. So there's an indication for you whether or not you did this correctly. Now, it's really, really easy to make a ton of mistakes here because you're actually foiling a whole lot of times here. Notice that after I drop down that 3, I already get a basically two terms here. I have a complex number here, and now I have to FOIL 1 plus 2i times 3 plus 6i. So there's a lot of calculations here in order to, get that next term. So it's not, or I'm sorry, I wouldn't take that one. I would actually take this 2 plus 6i times 1 plus 2i to get 10i minus 10, and then continue on. So you're doing a lot of work the first time around. However, when you take your second root, 1 minus 2i, that conjugate here, and you use your resulting polynomial, here, this is much easier to do this synthetic division. So you multiply it by the 3 here, and look at this. This is actually going to cancel out here to become just a real number. So 5 times this ends up being 5 minus 10i. These cancel out again, leaving you with negative 12. And then when you distribute here, you get negative 12 plus 24i and a remainder of 0. So this time it was really, really easy, right? I'm left with 3x squared plus 5x minus 12. Now you're going to set that equal to 0. Okay, so essentially what you've shown so far is that the factors of that original polynomial are x minus 1 plus 2i and x minus 1 minus 2i multiplied by this quadratic. Now all you have left to do, obviously, is just solve this quadratic. Okay, so I would look to factor this quadratic. It's going to factor into 3x minus 4 and x plus 3. And I get solutions of 4/3 and negative 3. So all of the roots, make sure you're listing all of them. Your solutions here would be 1 plus or minus 2i, the 4/3, and the negative 3. All right, so that's one option. Now again, this is actually, I paused the video, but that would take me, I think I probably took a good 3 minutes to do that, just to make sure all my signs were right and I didn't, mess up. Especially when it's really frustrating when you end up with a remainder and not 0 here. You're going to be like, oh my god, and then have to find all the little mistakes. So there is one method for solving it. Now, for me, an easier method, and it just depends on what you like to do, an easier method is to actually either multiply this out to figure out what that quadratic would be, and then use long division. Okay, so either way, you're going to have to do some tedious calculations here. So one of the things you could also do, instead of having to, FOIL all of this out, one of the things you could also do is use that idea that your b term is the opposite of r1 plus r2, right? These are just roots. And your C term is R1 times R2. So all we have to do here is add 1 plus 2i and 1 minus 2i, and then take the opposite of this to get my B term. Okay, so obviously the 2i's cancel, and I'm left with -2. So B is equal to -2, and my C value is 1 squared minus 4i squared. So my C value is 5. Therefore, the quadratic that would factor that original is x squared minus 2x plus 5. All right, now that I have this factor, right, I'm going to take that original polynomial, this 3x to the 4th minus x to the 3rd, that original equation, polynomial, and now I'm going to use long division to find the other factor, the remaining factors. And lo and behold, this remaining factor ends up being 3x squared plus 5x minus 12. All right? So essentially you end up at the exact same spot that you do if you use synthetic division. But to me, it's easier actually to do this. Okay? It's easier to do the long division calculation, but really it's up to you. You could do this, and once you see a problem where you have to do that, you're going to see what I mean by how many calculations. But if you stick that out and you get through that and you get a remainder of 0, this one at least is much easier, much quicker. So you have a little bit of front end work, but then the rest of the problem becomes pretty simple after that. Whereas here, after you do a little bit of easy calculations, then you have to go through all of this long division stuff. So really, it's up to you what you want to do. In number 2, I'm going to take the easy way out for me and do the second method that I went over with you, the one that was on the left-hand side. And we're doing basically the same idea here. It says find a quadratic equation with rational coefficients and a leading coefficient of 1 such that one of the roots is 2 plus 5 root 3. So since R1, root 1 is 2 plus 5 root 3, that means we have another root, using the conjugate of that, 2 minus 5 root 3. So I am now going to take R1 times R2 to find my C value, and I'm going to add R1 and R2 to get the B value. So I'm going to take the opposite of that. If I multiply these out, I end up with 4 minus 5 root 3 squared, right? 2 squared minus 5 root 3 squared. So be really careful here that you don't mess up. So you have 4 minus 25 times 3. So we have a total of -71 here. And that's my C value. Okay, my B value, if I add these together, the -5 root 3's cancel each other out, I'm left with 4. So B is equal to the opposite of 4. Now, that means that the original quadratic was x squared minus 4x minus 71 and equals 0, since it's asking for a quadratic equation, not just a function, but a quadratic equation. And really, I'm done because I have a leading coefficient here of 1. And so I've answered the question in terms of what it's looking for. So although problem 2 seemed like it was a very basic question after completing problem 1, really the two problems are very similar in how you are using the conjugate roots in the rational roots theorem. Problem 1 was definitely a beast of a problem, and that's because you have this to the 4th degree. So you're finding 4 distinct roots here. So really the concept here is similar, though. We just found the conjugate, and then we used either the linear factors and multiplied those out to find your quadratic equation that you then, or your quadratic polynomial that you then used long division to find the resulting quadratic, and then we factored this to find these solutions over here. Or you could use synthetic division. It's really up to you, whichever one you do. Remember that this one is going to be tough at first, but then the second time you do it, it gets really easy. So it's up to you whichever method you want to choose. So let's talk next about Descartes' rule of signs. Descartes' rule of signs states that for any polynomial f of x, you can use the number of sign changes in f of x and f of negative x to predict the maximum number, I should say, of positive or negative real roots. Okay, so basically all that you're looking for is to take a look at your original function and then look at how many times it changes from a positive to a negative sign. And that's going to indicate to you how many maximum positive roots you would have. Then you would do the same for the opposite of x, so plugging in negative x in your function, test to see how many times it changes from a positive to a negative, and then that will tell you how many maximum number of negative roots you might have. So let's try some problems here applying that rule. Alright, now notice the directions here say list all of the possible combinations. It doesn't ask us to solve, it just says list all of the possible combinations. All we need to do then is look at f of x and look at the sign changes. Now this is a positive, so it's going from a positive to a positive, which means there is no sign change. Now it goes from a positive to a negative, so there's one sign change, and then an additional sign change here when we go from that negative to the positive. So here we have two sign changes, which means that we have a maximum of two positive roots. Okay? We also will then test f of negative x. And if I plug in negative x here into this function, and you take negative x and you cube that, you'll get a negative x cubed. When you take negative x and you square it, you'll get a positive x squared. And then here, you'll get a positive x and then plus 1. So when we look at our sign changes here, we go from negative to positive, so there's one sign change. And then we don't change anymore after that. So one sign change means we have a max of one negative real root. Okay? So after doing that, we're going to make a sign chart. In our sign chart, we're going to have our possibles, our list of possible positive roots, negative roots, and then imaginary roots. Now for the imaginary roots, it's very, very important to remember the fact that imaginary roots come in pairs. Okay? So these always come in pairs, meaning that in this column I should only see 0, 2, 4, etc. Okay? Because they have to come in pairs. So here we've got a, for the positive possible roots here, because remember it has a max of 3, so going across we should have a total of 3 roots. I have a possibility of 2 positive roots and only one negative root, because I have a maximum of 1 there, and then of course 0 imaginary roots. Now let's say that I were to increase the number of imaginary roots. Remember, it can only increase by 2. So that means that I can't have any positive roots, and I could still have one negative root. And the reason why is because this number also has to decrease by 2. Okay, so the number of positive or negative roots must decrease by 2 to accommodate the fact that you have these imaginary numbers. Okay, so the option of, let's say, 1, 0, and 2 does not work, because this number must decrease by that max by an even number. So for example, let's say you had a possible 5 roots. So the max is 5. Well, then the next possible combination of positives would be 3 and then 1. So these would be your only options, because this has to decrease by 2 essentially. Okay? So this would be the possible combinations here, and that would be actually your answer to show the possible combinations of your positive, negative, and imaginary roots. So let's do another problem. So that makes it a little bit more concrete for you. I'm going to test now f of x and see how many times the sign changes. So here I've got no sign changes at all. So that's 0 positive roots. Okay, when I test f of negative x, I end up with negative x cubed plus x squared minus x plus 1, which means I now have 1, 2, 3 sign changes and a maximum of 3 negative roots. So I make my sign chart, positive, negative, and my complex non-real, so my imaginary roots, and I'm going to have 0 positive roots and a max of 3 negative roots, which makes me have 0 imaginary roots. Now remember, they can only come in pairs, so I can have 2 imaginary roots and 1 negative root while still having only 0 positive roots. Now these are my only options, since I cannot have 3 imaginary roots. Alright, so this is my only options. Now let's work on a problem that's going to be a little bit tougher. You on your own should pause the video and work on number 5 here. And I'm going to work on number 6 with you guys now. Okay, in number 6, if we take a look at f of x's sign changes, we have a positive to a negative. So 1, 2, 3 changes. So I have a max of 3 positives. When I check f of negative x, I'll have negative x to the 5th, negative x to the 4th, positive 3x cubed, positive 2x squared, negative x, and negative 5. And now I have 1, oops, I'll skip there. So starting with a negative don't think of that as a sign change. So you started with a negative, you're still at a negative, there's no sign change yet until here. So we have 1 sign change, still no sign change, then 2 sign changes, and then we're done. So there's a max here of 2 negative roots. Okay, so here we'll make our sign chart. In total, we should have 5 roots because this is an x to the 5th. So I have my positive, negative, and my non-real complex, my imaginary roots here. So I can have 3 positives, 2 negatives, and 0 imaginary roots. And again, these can only increase by a factor of 2. So I could have 2 imaginary, 0 negative, and 3 positives. Okay, so there's one of those options. Now, I can also decrease the number of positives by an even number. So remember, you can't have just 2 positives. You would have to go down to 1. So if I went down to 1 positive, I could have 2 negatives and 2 imaginaries. Okay, so there's another option. If I went to 1 positive, 0 imaginary or negatives, sorry, I keep switching the words around, then I would have 4 imaginaries. Okay, this list is all of the possible combinations. Okay, so basically these numbers here should always be different, either the same or different by a factor of 2. Okay, so essentially that's really all you're doing on all of these problems. This would be my answer, showing the list of all possible combinations of roots. Alright, please try 7 and 8, especially if you think any of this is confusing. Please try 7 and 8, okay? And good job. I hope you had a fabulous Thanksgiving and you ate a lot of turkey. I'll see you guys on Monday.